Okay, I tried to go as fast as possible. And then we get quite close. So, anyways, I'm Zahid from Citadel in France, and the presentation today quickly will be about blockage effects in mmWave small cell networks. So let's have a quick look. Just to give you an introduction, the idea is first to introduce a hybrid deterministic and stochastic model and some motivation why this is required. Next, we will have some simulation framework and scenario for the simulations that we've conducted. The user body obstruction model, so we're looking at the obstruction caused by the human body, and along with some single cell and two cell simulations. And eventually the main goal of this paper was to see the small cell network performance or the global performance, and along with some conclusion and perspective. So blockage modeling, the motivation has been to upgrade the ray-based models that we have right now to run reliable outdoor millimeter wave communications. Because we know at millimeter waves, things are different, the wavelength becomes very small, so we will see why it changes. So the typical scenario is like shown in the picture. We have small cells located on top of lampposts that you can see, and there could be various obstructions in this environment. So of course, traditionally we know that there's obstructions like buildings, for example, but at millimeter waves what is also interesting is the facade of the building. So because the wavelength becomes so small, smaller details on the building could also make a lot of difference. Further, it's vegetation, so there's trees everywhere, and there could be a lot of blockage due to these. Next, we have urban furniture. So for example, if the small cell is located on a lamppost, the lamppost itself could have some obstruction due to this, and there could be some scattering and so on. So this is interesting to see. And then we have mobile obstructions. So for example, large vehicles which are moving in the environment, which could cause some kind of obstruction. And eventually, human bodies themselves. So if you're looking at a network with users, it's omnipresent. You will always have bodies around, and there will be some obstruction due to these. Here's, you've probably seen this before, an earlier study that we had done comparing sub-6 gigahertz and 60 gigahertz network. So here we see some buildings in gray, and here we have large vegetation blocks in green. And we can see at 2.4 gigahertz, there is some shadowing behind the large vegetation. But at 60 gigahertz, there is no signal behind. So basically, what happens is when we move to higher frequencies, the same obstruction becomes opaque. So what we next wanted to do was to look at, we see that there is an impact. So we wanted to see if the impact exists with single trees. So traditionally in map data, you only have large vegetation blocks. So we put individual trees in the environment and try to look if there is an impact. And clearly, if you can see at 60 gigahertz, there is an impact due to individual trees as well. So the question is, what other objects we need to consider? As we know that at millimeter waves, the electrical size of an object becomes important. And whether we need to use deterministic or stochastic approaches, and how can these be modeled? So for human body blockage scenarios, there could be different scenarios. The first picture on the top left is, let's say, when a user is located very close to a large vehicle, so for example a bus. The bus would cause obstruction, but it could also be due to the human body itself. So in the second picture and the third one here, it's self-body obstruction, so it's the obstruction caused by the user himself or herself. And last, we could also have human obstruction, which is caused due to a crowd. So it's not the user himself, but people surrounding a particular user. Blockage impact. So here we have the azimuth arrival angles versus delay for a particular scenario. So this is at a fixed location, we have a user. And what we have here is all the rays coming into the user. So without no object is all the rays we have. But we see that at vehicle obstruction, some of the rays are missing. But what is also interesting is you see here, there is additional rays that is found. That is basically the reflections from the vehicle itself. Same thing for body obstruction, some of the rays are missing. And when we look at both user body and vehicle put together, we can see that the impact can be very large. So to give a quick example, you can imagine if a vehicle is blocking some signal from one side, you can be connected to another small cell, but imagine the body blocking even that cell. So you're basically in a cannon without any signal. You could probably have outage. So to give you an overview, our study is done at 60 gigahertz, millimeter wave frequencies, channel modeling. The idea is to propose a ray-based hybrid model. And the reason why we need this is because obstructions like buildings and vegetation are deterministic in nature because they're fixed in a particular location. You can find this on map data. But obstructions like large vehicles and human bodies are moving. They're more stochastic in some sense. And if you really want to model it in a deterministic way, it could be quite computationally extensive. So you require some kind of stochastic component to do this. And of course, the idea is also to use some beamforming and beam steering antennas to do all of that. And in the evaluation, what we need to see is that traditionally we've looked at map data, which considers open squares, straight canyons, things like this. But for this paper, the idea is to look at the global performance of the network. So we have a small cell network, and we want to look at the performance of, in general, for all the users, and not a particular scenario. So in previous studies, we've looked at particular situations where there could be large impact. So now it's about the whole network. So here's the simulation framework. We have a small cell network. It consists of 18 small cells. And there you can see a picture from Google about the same area. It's 3D buildings that we have. And also what is interesting to see is that we've considered individual trees in the environment, which gives a bit more detail. And here you can see in purple, we have some buses, which are the large vehicles. And the users are on the blue lines. I don't know if that's visible to you. There's some blue lines here. These are the pavements, so we have some users on these. So the area is about 0.09 kilometers square, with an average inter-site distance. The distance between two small cells is 78 meters. Of course, the red dots are the small cells. The ERP is 40 dB, it's fixed by FCC. And all the small cells are located on lampposts in the street at 7 meters above the ground. And all the antennas have steerable maximum gain of 18.5 dBi and half power beam width of 22 degrees. And the transmit power is 21.5 dBm. So the users are randomly located along the pavements. So this is one stochastic component that exists. And the demand of the users is 15 Mbps. And the active user density is, depending on situations, 200 or 1,000 users per kilometer square. And the traffic considered is non-full buffer. So quickly to the user obstruction model. So the question is, if you have a human body, how do you model it? So there's various methods to do it. And if you look at on-body scenarios, so where you have a device on the body, it's quite extensively seen. And that's kind of where we take the model from. We've considered the human body as a cylinder, a uniformly dielectric cylinder. So that's the top view. And we can see that if that's the incident propagation path, which is the transmitter is located in that direction, we will have the user body. And we have the antenna, which is basically the UI or the mobile. And this can be oriented in any direction. So what is interesting is that if you are completely right on the other side of the specular path, you might have some blockage. But it's also possible you're at a different angle, and this has to change. So it's not yes or no. Next, for this case, for instance, we've considered a shadow region. And if the antenna is about 20 centimeters from the surface of the body, or from the center of the body, it's about 40 centimeters, the shadow region is about 60 degrees. So in this region, basically the shadow region is the area where you cannot have a line of sight component. So if you look on the picture, it's not possible in this area to have a line of sight component. And basically what it means is that there will be some diffraction, perhaps from the sides, and the signal is coming in. Next, the random positions of the users was a stochastic component. The next stochastic component is also the random body orientation, so how the body is oriented. And we need to look at the diffraction. So there's various diffraction models that have been used in literature. One very popular model is the knife edge model, or the single knife edge model. Here we have the gain, and this is the orientation, phi. And if we look, for example, at a shadow boundary of 5 millimeters from the surface of the body, we see that the shadow region starts at 102 degrees. And we see that the single knife edge model underestimates the shadowing. And how do we know that? It's because we also considered, we looked into the literature, and there was a uniform theory of diffraction, UTD-based models, especially the creeping wave model, which considers that the millimeter wave, the wavelengths are so small that the human body could be an infinitely large cylinder. So the wave would travel as a surface wave on the surface of the body. And we see that it's quite different from the single knife edge model. But again, it's quite computationally expensive. So what we looked at was also an old ITU rounded obstacle model, which was used for larger objects, but at lower frequencies. And when we compare it with UTD-based models, their performance is quite similar. And basically what it is an extra attenuation, which is added to the single knife edge. So it's quite simple. So of course, this was for 5 millimeters from the body. So this is because this is actually checked via measurements, the UTD-based models, the creeping wave model. And we want to use it for 20 centimeters, which is a user holding a mobile in his hand, for instance. So we've used the red line. For the single cell simulations, so you saw the whole network earlier. So we've considered a single cell, shown by the red dot. And I don't know if you're able to see, there's a small area around it that we have considered, so it's not the entire area. And what we look at is here we have the cumulative distributive function, CDF. And what we see is that there is reduced interference, or reduced SNR level, due to the body obstruction, which is expected, but it's only about 3.5 dB at the 10th percentile, which is perhaps not as important. The most important ones are very, very small. So basically, the idea is that there could be body blockage in a fixed scenario, but if we look at a more realistic scenario when you might have it, sometimes you might not, and so on, the impact might be smaller. So we look at a two-cell scenario now. You see the two cells there. Here, first we look at the interference. So what is interesting is that the interference also decreases. So this is a positive impact. This is something we want. So at the 50th percentile, it's about 6.7 dB. And that's basically because between two cells, if there is blockage, it's not only blocking the signal, but also the interference level. So the interference is blocked, and therefore the level goes down. And this actually impacts the SNR in turn, because the SNR difference is not so much as well. Another thing we consider here is optimal cell selection. So what this means is that the user is always connected to an optimal cell. So basically, if there is a body blockage on one side, the user will connect to the next cell immediately. So yeah, and it's about 2.9 dB at the 10th percentile, which is lower than the last case. So now to move to the whole network simulations, we have the entire network, 18 small cells, including the vehicles and the obstructions. Another interesting thing is when I say no objects, it only means no stochastic objects, so it's humans and let's say the vehicles, but the buildings and the trees and so on are always included. So here we have a user density of 1,000 users per kilometer square, and the stochastic components are the user locations, which are random, but also the user orientation and the vehicle locations at each iteration. So the average interference, here we can see, is about 1.9 dB, which is mostly caused due to the user obstruction. Now why is this due to user obstruction? If you carefully look, the placements of the small cells are also very interesting. So basically, if you simply take the two small cells and move it to the opposite sides of the street, what effectively you're doing is reducing the interference of the street. So the user can always connect to everybody on the pavements. But
say it again, you do what?
So if you move the small cells, let's say that the small cells are on the same side of the street, and now if you move them to opposite sides, then all the users on one street are able to communicate or link to one cell, and all the others on the other cell. So what you have done is effectively reduced the blockage effect of all the obstructions in the street itself. So if you carefully look, they're slightly displaced, some of the cells, and that's the reason. Next, of course, the SNR is even lower. It's about 1.1 dB at the 10th percentile. So the blockage effect in general is not as much as we were expecting. But, of course, it's not a complete study to come to conclusions. Hybrid models are required to include some dynamic or non-static obstructions in the channel, like human body, vehicle, so on. Obstructions can also bring positive effects like reduced interference levels, which is good, which is what we would like, but with better intercell isolation. Significant impact is only seen on the worst served users, so if they're cell edge users, they would have some impact. The physical locations, like I mentioned, makes a lot of difference in small cells, where by just placing them diagonally opposite sides of the street, you can reduce the impact of obstructions in the street. The blockage impact could be high in certain mmWave specific scenarios. So if you look at one user, so in a previous study, we looked at the users maybe at the bus stop, and like I mentioned, if there is a bus and then the user body itself, and the user device is stuck in between, this could be a very large impact. But globally, it's not as much. Of course, these are some initial studies. We need to look at more obstruction components, for example, due to a crowd, due to street furniture, and so on. So that's about it. Thank you.
Okay, and can you go to the slide with the whole network simulation? No. The results with the whole network simulation. Sorry. That's it. Okay. I'm not sure that I'm seeing well, but is the same the graph with user body obstruction and user body and vehicle obstruction? You say you get the same results.
Okay, so it's not so easy to see here.
Yes,
so yes, they're very, very close.
Very close.
Very, very close. And the reason, like I mentioned, is because the small cells could be, if they're slightly displaced. So if you have, let's say, both the small cells on one side of the street, and then there is a vehicle in between, and there is a user on the other side, he will have some blockage impact due to the vehicle. But what happens when you move this small cell to the other side of the street, then all the users on this street are always connected to the best small cell on this side, and all the users on this street are always connected to this small cell.
Okay.
Then everything in the street, the vehicle, for instance, does not have such a large impact then.
Okay.
Yeah.
That's an assumption, let's say, that if we move the base station.
No, it's actually part of the recommendations of the standards. It's not still in part of it, but there is a lot of talks about this. And so it's most likely that if you have a small cell network and you design it, it should be designed so that they are not on the same side, for instance, so that it removes this.
Have you considered self-organized networks which can help on that?
No, but it's very interesting because all we need to do is we have a small cell network now, and we just need to have intelligence.
Yeah, exactly.
To the network.
Because
and
I think the self-organized networks can solve this. You know, you can play with your network. You're flexible with your network in these cases.
Yeah, absolutely. But again, higher level a little bit. So, and it's most likely if you have a network like this, it will be something like this. At the moment, we don't even know what kind of networks we might have for millimeter waves. So if it's just going to be 2 or 3 small cells, or a small network like this, or we don't know.
Can I add 2 things more?
Yeah.
So that my comment for your presentation is just that it must be a bit bigger your graph, just to be more obvious that the same or is different.
I don't know if I really put it all the way also, if you're able to see it. Because
I don't know.
The first time I looked at it, even I was surprised, so I had to go and see the data, if the data is different, and the data is different.
Okay. I think changing the color of the first 2 graphs will be enough.
Sorry?
Yeah, maybe
no objects and also body obstruction. If you change the color, it could be enough.
No, blue and red,
they are just overlapping almost the data.
So the red and the dotted blue line are overlapping.
it's fine, right?
Yeah.
No, what I mean is, if you change the color of the no objects, for instance, it's fine because the other ones, it's evident that they are one on top of each other, right? You can see 2 colors on them.
Yeah.
The point is that you don't know if the user body obstruction and no objects, which one is which, right?
No,
Or
it's
do
a
you
dotted
see that
line.
correct?
You see, for example, here it's a dotted line and it's a solid line.
The other one
If it was solid, it would be totally blocked.
Okay. Anyway.
The third thing is that in the beginning you made some assumption about the distance between the base stations, the user demand, something like that in the beginning when you set up your scenario. Here, about the users.
These are not assumptions. So, in a previous work, we designed the network. So, with our tools, we are able to do network level simulations as well. So, we looked at the coverage, and we looked at, of course, we've not randomly placed the small cells. So, the small cells have been designed. So, a network is designed with, of course, some things. For example, EIRP, it's fixed. We cannot.
I'm asking actually if we increase the demand of the user, we're gonna see this is gonna change something.
It's an interesting question.
Why you choose 15 megabps, for example, first of all, and then if we change it, it's gonna.
It's an interesting question, but that's the biggest assumption probably with millimeter waves is that we have too much capacity.
Okay.
So we have too much bandwidth, we have too much capacity. So at least right now, at least for a few years, we don't have this question, I guess.
Okay.
Yeah.
Yep.
First, I would like to comment on the first slide that I really like that you put a lot of pictures. It's a very positive comment, and I was able to follow it very clearly. And something else that I want to ask, in the slide, I think it is one or two slides after this for the user rate and interference.
User?
After this, when you talk, here, when you talk about this 3.5 dB difference in reduction in SNR, can you tell me, do you remember how much is the ratio of the density of the base stations and the users? I mean, approximately for how many users per set we're talking about?
It's 20, I'm not so sure right now, but I think for a single cell, so it's a small area, so it depends on the user density. So like I mentioned, we could use, we have used either 200 or 1000. And in this case, I think we have used 200 users per kilometer square. So this is a particular area. So there is an area is fixed, and it's just the density of the users that we have used. So in that area, there will be so many users.
And the ISD was 76 meters, I think, something like this.
No, that's the intersite distance. So the area is about, I think, 0.1 kilometers square. So it's not so large.
Okay.
And it's not the entire area. This is, in this case, it's only for the one cell. So the actual area under consideration is this blue box. I don't know if you're able to see it.
Yes,
it's a very small area.
Because I was finding it strange that, because I have read that in millimeter waves, the obstruction from the body can be up to 20 or 40 dBs.
Yeah.
20 dBs, I think. And
No, higher. This is the diffraction losses. So we see that gain or loss can be very high in some cases. So basically, if you have the specular reflection and you're holding the phone right here, maybe you will not have any signal at all at very high frequency.
Yes, exactly. So I was trying to think maybe how much, for example, if the users per cell are not a lot, I was trying to see the number. Maybe, I don't know, I was surprised that I saw such a small difference, as you also said, of course, in the presentation.
Yeah, because again, we're trying to look at the global impact. So as I said, if it's a single user, so if it's only one user standing at the bus stop, and we're looking at the impact of this user with a lot of users around him, in this case, yes, there will be a large body impact, could be.
Yes.
But this is a global impact. So when we do the whole network simulations, we have a lot of users in the environment, and the results are for all the users.
Yes.
It's not a particular user. So in this case, with some, like I mentioned, that if the small cells are removed, things like this, the impact could be quite less. But of course, it's not considering everything. So for example, the facades of the buildings, things like this, it will change some things, and that's, we need to see more.
Okay.
Some users might also be at a preferable angle, and some might be at a worse angle, so
Yeah,
you include everything. So
Yeah, but that's exactly the effect that is simulated here, is that some are served very well, maybe some not so much.
So you model the angle of blockage. Do you have a statistical model that you use for the blockage angle or something like that?
Yes, so that was the shadow region,
Yes,
so we
shadow
have a
region,
shadow region, and
yeah.
it depends where the
Yeah.
user is located.
Just one question for me to get some intuition. In this plot in slide number 4, with a plot that I've seen way too many times, this one. What's the area of this picture? Just to get some intuition of what we see.
Oof, this was before I joined in, so I'm not exactly sure about the simulation. But why? I don't see why the area would.
To connect the effect of the blocking in terms of distance, like in actual.
So the effects of distance, so the receive power is relative to the receive power. So here we are only looking at the blockage
Yeah,
impact.
of course, yeah, but also, for instance, in the small cell you have the small cell that you consider. What's the radius of the small cell, for instance?
Radius of the small cell.
Yeah.
So the distance between the small cells, average in the network, is about 78 meters, and there is no. So we have not considered mobility. So there is no handover. So there is no boundary considered as such here.
Yeah, yeah, that's why I was asking about that. Yes.
So it's 40 meters, you're saying, of radius. In that case.
No.
Half of
It
this.
depends because, for example, let's say that a user is located at
Without obstruction.
10 meters. Yes,
Without
exactly.
obstruction.
No, but it's not. Yeah, it will be somewhere in the center, but it's an average intersite distance, 78 meters. So in some cases it's larger, so it could be different.
Okay.
Some it's closer, so it will be different.
Depends on the density.
Do you consider the obstruction of, the obstruction of the body itself is clear, but do you consider obstruction of other bodies?
Next, people. It's
Okay.
it's the crowd obstruction. It's
Yes.
something very interesting. Again, we need to look at the impacts, but again, there is some positives and negatives. So what I could quickly say is that, of course, there would be some losses which are due to diffraction to the crowd, but there could also be some reflections to the body, which could be some positive things. So it's much more complex than it seems. So we need to.
Another question is, when you change the location of the small cells to avoid this blockage effect, are not you removing the effect of the blockage and then somehow reducing the capacity of the new channel model? You incorporate in your new channel model some random effect. And one of it is that you introduce vehicles, right? That kind of structure. If you change the base stations, you reduce this effect, or you can even neglect it.
Yeah.
At least the figures show that.
So if we look only at this presentation, it could be interesting. But the presentation at Kamad, for instance, was only about the obstruction due to the vehicle.
Yeah.
So we looked at individual cases when it's happening. So the impact would be quite large, in the range of 20-25 dB in this case. So here, the aim, like I mentioned, was to look at the global performance. So what happens on an entire network, not in a particular situation. Of course, in a particular situation, even in this network, it's possible that some users.
There is I think that there is a typo. I'm not sure in the graphs. In the y-axis of the graphs, I think there's a typo. Is it possible? I'm not sure.
Is it possible? Good question.
Here, the figure on the right, for instance, is correct. The y-axis, or it should be inside the parentheses. Because I've seen this in other figures as well. The same problem. It should be inside the parentheses.
less than or equal
Less
x.
than x between the.
The
within
right
parentheses.
parenthesis just.
No,
Yeah.
it's the probability of the SNR, which is less than or equal to x.
Right.
No, it's the probability of the
parenthesis should
SNR.
The interference one.
Medium x, right?
Not the rift.
Above x.
Maybe the
Ah,
position on the
you
left.
mean okay?
Yeah.
Okay.
Yeah.
The rest of the figures, just move it. Go to another figure. Like
Yeah,
this.
yeah.
You see?
Yeah, but it's
here
the same code, so it's
Ah,
going to be
okay,
the same.
Anyways, yes, here
But-
it's the same.
Okay.
It's the right
This is
one
what I'm
here.
saying.
This one is the correct one here.
Well, no, what I'm saying is that the y-axis is, there's a typo here, right? Or not? In both.
This one is the right one.
No, but
There
this
the
is right.
previous one.
This is correct.
So this
This is
right.
correct. The previous one.
Yeah.
The previous one. This one. The right parenthesis
The
on the
parenthesis.
interference.
Yeah.
The figure on the left.
Yeah.
Yeah.
Yeah, it's okay. So maybe the font, I don't know exactly if people in the very back can see because it's very light chan. And these things you said that maybe you cannot see, and honestly I cannot really see the square. Okay, but these are all
I think this is from the Cyrodiil template.
yeah, this is the Cyrodiil template.
But he can still make the light blue a little bit darker.
Yeah.
Zahid, X is then percentage or dBs? This is my question.
It's percentile.
Okay.
It's percentile. It's a CDF.
That's fine.
Because you were thinking the dB that.
I was thinking
okay.
the probability that the SNR is lower than a given value of in dBs. That's what I was expecting.
Okay. No, I have some general questions. So, what I understood that you do, I mean, if you tell me, okay, you have this fancy super mega simulator for Cyrodiil, okay, so you plug everything inside and you get such amazing results, okay. But explain us exactly, I mean, what your specific contribution on this simulator is. So, what did you implement? What did you implement? I mean, did you implement the blockage model for the body? Did you develop a new blockage model for the body? Did you test the different blockage models for the body exactly?
Yeah, so the simulator is, we've been doing it for traditional frequencies. So right now the study is to look at millimeter waves. So we need to add all of these components one by one into the simulator. So we're doing two things. So we're looking, so there is a simulator already, but we're also developing the simulator through research. So when we do the research work, we see something interesting. So all of this is already implemented in the Cyrodiil simulator. So we've actually built the
No, I'm wondering if you are developing new models to be included in the simulator, or if you are trying to, take models developed in papers and try to enhance or enrich this Cyrodiil simulator.
So I think the main aim, of course, is to have the simulator run millimeter wave outdoor simulations, however it is.
No, I understand.
But,
Company-wise, I understand. It was
yeah,
just to-
depending on the application, we could have that when something is not as we want it, of course, then we are having something on our side as well.
No, just something for me to understand, in the context. Okay. I mean, the other thing is, if you go to the conclusions, so it's very good. I mean, to have this kind of simulators because you can really get very, very good results. But if I look at the conclusions, somehow if I read them, I found them that somehow was expected. So physical location or topology of the base station can reduce the impact, but you don't tell me really how much on average you can reduce, what kind of, it's not really precise, blockage impact could be high in certain millimeter wave specific scenario. Said like this, you said, okay, what does it mean?
Yes, but
I mean, exactly means everything and nothing. You know what I mean? As a researcher,
So, like I mentioned, so the thing is that when we looked in our previous study, for example at Kaplan, in a specific scenario you might have blockage. When we're looking globally, it's not as much. And of course the study is ongoing, so it's not finalized, so we don't know that, okay.
I get a lot to know the comment that Panagiotis did, if you change the density of users, the density of users, for example, if actually you change this angle that you were saying for the blockage, for example, your results will change. That's also what you said. So if you change the density of users, and if you are taking into account the impact of the blockage that other users can create on your signal, etc. So it would be very nice to have a result that says, that gap, but as a function of, for example, the density of users, as a function of the interset distance of the femtocells, as a function of the average number of buildings in the environments, as a function of the angle of this region that actually can block you, because this gives somehow results to other people that then, you can reuse. Yeah. So you know what I mean?
Yeah.
That's the kind of results that I was kind of expecting,
Yeah.
Rather than maybe you are doing it.
Just to quickly say, like what Panagiotis said, if we had we increase the user densities, of course this could be the case, but the values we have chosen are also not random. They are standard values that they use. For example, maybe in rural environments it's 200 users per kilometer square.
Yeah, but
and
exactly.
Urban
that's exactly the comment that I would have seen here. In suburban environments and with this scenario, maybe you cannot say this to us. Okay, I can understand. But I mean, that's the kind of scenario that maybe are interested, no? In an urban area like with these characteristics, I get on average this. So.
Yeah, but it's also, I think, related to your previous question about the channel models itself. So if you look at some winner models and so on, there's some values that you can find very clearly for different scenarios, how it can be. And of course, it's also interesting for us to see what happens at different situations. The second, about the body blockage, this is, it will not change when, so the shadow region depends on the distance of the user equipment from the body. So of course we've used 20 centimeters, so this is one assumption. If we change this, it could change a little bit, but the question is, when we look at the diffraction loss, for instance, it's minus 80 dB. You don't have signal at minus 40 or minus 50, so sure, it could be, no, the point here is only that in millimeter waves, maybe in some cases you might have signal, sometimes you might not have anything, so it's a very...
No, I understand. I mean, this is totally understandable. I was just thinking if, you could get some, parametric results, then that was the, maybe it does not make sense, I don't know, you want to use these specific values, etc., but I was just wondering. Yeah. Because I mean, all these simulations, all the time you run these simulations for 78 meters of intersite distance of small cells.
No, it's for, so we designed this network in a previous study, and we are using this right now. Of course, if we design another network, it could change. So it really depends.
I'm telling you because of this. I was, for example, I did these kind of simulations or mathematical frameworks for millimeter wave, and I was in a conference, I was presenting these results, and I said, I used this channel model from Rappaport. If you don't have an intersite distance of at least 50 meters, you will never outperform conventional cellular networks. So I said I was using like 28 and 73 gigahertz transmission against the 2.5 gigahertz transmission, and I said if the intersite distance of millimeter wave cells is not at least 50 meters, the conventional cellular systems will have a much better coverage than the millimeter wave cellular systems. So, okay, everybody said, okay, I understand the concept, I understand your results, but don't make this point too strong, because if you are not in New York, in Manhattan, and you are in another place, I mean, this optimal cell radius is going to change, you're going to get all different results. So, people would be interested in knowing, some case studies, some reference scenarios, what you can expect on it. That's the reason I'm asking. Yeah. I got the same question that I asked you, that's the reason.
No, I also received the same question at the presentation. It's because also any simulation is heavily dependent on measurements, and we need more measurements all the time, of course. The more measurements we have, the more things it can be. So also, like you said about New York, there's some measurements at Bristol, where Bristol is apparently a very hilly city. So it's interesting for them to look at what happens on the hill, because then this can make a lot of difference, and so on. So yeah, it can depend from place to place and based on measurements. So.
Yeah, for sure. Yeah. Okay. It's done. Thank you. Who's gonna be the last one?